Good afternoon, everybody. My name is Dean Weber. I'm the Chief Technology Officer at Mocana, and welcome to our presentation.
And my name is Joe Doetzl. I'm from AVB, and I'm responsible for cybersecurity in our grid automation business unit, which includes protective relaying, wired and wireless networking, SCADA EMS products from AVB.
So what we're here to talk about today is securing industrial control systems and what is actually involved in securing the control systems themselves, not necessarily the network frameworks that they're attached to or the communications protocols that they're using over WAN or other forms of terrestrial and non-terrestrial communications. This is all about securing the endpoint and validating that its structure is trustworthy and building trust into those platforms.
So one of the use cases that we want to talk about are the business drivers and why we're seeing such an explosive growth in these technologies. And I want to talk about it just a little bit from the ABB perspective, and particularly from our electric utility customers. And why I think this is important is because many times for us in the security arena, we're focused on, oh no, this is scary. But the business drivers are so compelling that we've got to find a way to utilize this technology to increase security and resilience rather than just try to stop it. Because that train is coming, we're not going to stop it. But just from our utility customers, it's so compelling. We reduced installation time and reduced physical materials. One of the examples that we like to use, a completely digital substation takes anywhere from 30 to 50% less copper than a traditional substation. I mean, that kind of math is compelling, and we're going to start seeing this infrastructure just explode and across the many use cases, reduced maintenance costs, reduced outage time across all of these different areas, DERMS or distributed energy resource management, how we're managing and our utility customers are managing solar power, wind power, et cetera. Our generation mix for electric utilities is much more distributed than it used to be. We're moving away from centralized power sources, for example. And when we look at this from a transformer perspective, so a transformer, for those of you who are not in the utility industry, is a very large, long lead time, expensive piece of equipment. These are massive, massive pieces of equipment that you would see in an electrical substation. And one of the use cases that we have around digitalization is asset performance management, and particularly with our transformers, we're able to take traditional SCADA data, combine that with online sensors, and then offline sensors, things like dielectric analysis, furans, et cetera, the types of analysis that people do on transformers to monitor their health. We're able to do this in near real time and provide analytics around predictive maintenance so that we can increase the life of these assets and avoid unplanned outages. And when we look at some of the use cases here, this is just one electric utility that's using a similar substation. We've got monitoring around 10,000 transformers across a electric transmission territory that is in 11 states in the US. 10,000 plus transformers, over 22,000 breakers, and about 4,000 batteries. Many of the electric substations, of course, have battery power as well to help manage the equipment. In just a year, we've seen savings of over $1 million due to avoided unplanned outages. We've been able to shorten planned outages and save an additional $2 million. But the big number is there at the bottom in avoiding asset failure altogether, nearly a $15 million annual savings. So this is compelling, right? There are valid use cases. And this is the type of software and asset performance management that our customers are beginning to embrace, that's going to cause an explosion of additional digitalization that we can help secure with some of the technology and interfaces that Mocana is bringing to the table. So I like to say that all of this doesn't increase the attack surface, but it changes the attack surface. So we need to, as security professionals, need to be cognizant that all of this additional technology brings with it a changing attack surface. And we need to make sure that we're deploying security controls at the right layer all across this. And that's something that Dean's going to help us with a little bit more.
Thank you. So at the end of the day, increasing or expanding or otherwise modifying the attack surface means change. And change means opportunity for people to do it wrong, to use the wrong technologies, to implement the wrong technologies, to configure the technologies incorrectly. All of those things are possible, right? So at the end of the day, what we're trying to get to is if you secure the device properly, and therefore that the data that the device is generating is proper, then you can make all of those analytics decisions that Joe just talked about successful. If you can't secure that, then you're basing your decisions and your analytics on data that may or may not be trustworthy. So what we're going to talk about today is how do we make trustworthy devices that are worthy of using those types of analytics that are being brought to bear. Lots of things about the devices that are difficult to manage, difficult to secure. Roots of trust, as an example. Most industrial devices are just starting to think about things like TPMs and other forms of trust anchors like TE, Trust Zone, or PUF. The whole concept of self-signed certificates, there's a reason that OpenSSL exists, and I would tell you that most of that's about the ability to self-sign certificates. The process of actually provisioning those devices with external root authorities using SCEP and OCSP is problematic because SCEP and OCSP themselves are problematic. Basically, if you want to use SCEP and OCSP, you have to either bring the device to a secured enclave or you have to take the enclave to the device. These are problems that you would exist or that do exist in architectures that are taking advantage of some of these new technologies that we have to address. Attestation is another big form that is a reality out there. How do you know the device is trustworthy? What measurements can you make? What measurements are available to you as to whether or not the device is trustworthy? And then ultimately getting back into the supply chain and tamper resistance or tamper proofing devices where you can use modern cryptography to do a lot of that. The presentation that was just in front of us was talking about how to take modern cryptography apart. Well, there's solutions to a lot of that stuff as well. Supply chain risks, I can't stress enough, whether Bloomberg's article is correct or incorrect, I can personally attest to that there are other forms of hardware attacks that have been successful, period, exclamation point. Supply chain risks are very, very complex. I was having a conversation earlier with a gentleman talking about the TPMs, right? And the Infineon TPM had an issue that needed a firmware upgrade to resolve. At the end of the day, what that was an option that Infineon had allowed to be used, which decreased the random number generator to actually allow the keys to be used in a way that was less secure because they were faster. So again, ease of use created the compromise that was the Infineon TPM issue. Should they have allowed that to happen? That's subjective. I'm not here to tell you they should or they shouldn't. People wanted it, they gave it to them. Then it turned out that it was vulnerable. So supply chain can start just about anywhere, but manufacturing of the elements, the discrete elements, the measurable elements in the supply chain, then into the manufacturing process, which is where companies like AVB then create the products that you're going to deploy to those substations and substation management systems, to actually then getting the devices in those substations and finding out whether or not they're still trustworthy, whether or not they were modified in transit, and then ultimately how do we manage those devices longer term, meaning those substation systems are going to be there for a while. I don't know what the average lifespan is there, but I can guess it's longer than a year or two.
Yeah.
by a considerable amount. So again, how do we continue to attest? How do we continue to manage these devices in secure fashion? And most importantly, how do we determine that they remain trustworthy? Creating trusted platforms is really about that, right? It's about how do we build trust into these platforms that is conveyable, that is validatable in terms of whether or not the device as built and as deployed and as operational is actually trustworthy. And these include things like trusted boot architectures and trusted BIOS architectures and trusted identities being deployed in these platforms. And there may be multiple identities in the trust chain. Infineon signs their TPM, Intel signs their processor architecture, AVB signs their platform. Right? Each one of these has a trust value associated with it that needs to somehow be chained together so that we can validate that all of those components not only existed at the time of creation, but still exist to this day. Firmware updates, another area of big concern that's been going on for quite a while now. Obviously, ESET released an article, I think this morning, talking about the natural extension from black energy 3 into this thing called gray energy, which is all about further compartmentalizing the black energy, which is loosely based on Duku and Gauss and a whole bunch of others that lead all the way back to Stuxnet. But all of these modular approaches to how to compromise a device and how to give the person doing the compromise options in terms of what they want to do. Do they want to wipe the device out and put a kill disk payload in? Well, that's been done. Do they want to upgrade the firmware so that they have a persistent presence on the device? Well, that's been done. So all of these things come basically through validated or insecure update processes to the platform. Platform wasn't built untrustworthy. Platform was built trustworthy. It became untrustworthy through operations. So how do we take that and build that into communications? And Mocana's belief is that that's done based on standards, right? Anybody that's doing this as a one-off or doing this on their own technology basis is going to have to convince a whole slew of us that that's a good technology. I prefer to be in standards-based, and Mocana does follow standards-based in everything that we do. Mocana Trust Platform, how we do all of this is we have an endpoint platform that's delivered as source code that gets compiled into the target platform. We've got about, 70 different chipsets and about 30 different RTOSes that we do today, and more coming online all the time. And our customers are doing some of that on their own. So we provide a porting guide, and if they don't want our services in terms of the porting architecture, they can do it themselves. This is the kind of the meat and potato slide about how it all comes together. I'm not trying to sell you, I'm just telling you how it works. The idea is that we have connected devices that are going to be made trustworthy through the use of applied cryptography. By accepting that those devices based on some root of trust, could be hardware, could be firmware, could be software, a lot of that depends on what the objective is. If you look at things like 62443 or NIST 853R4, soon to be R5, these are architectural models by which control objectives are defined based on an outcome. That outcome being how secure do you want to make the product. So the idea is that you build a platform, you apply security to that platform at build, you build it in such a way that it can be attested to, and then at the back end of that, you have to have some kind of management framework. So Mocana's goal with AVB is going to be that the trust center architectures are going to be integrated into their device management functions so that they can actually take advantage of the security underlayments and still provide their customers with that single pane of glass that is the central office management or the substation management type architectures that is where the real money gets saved. And then obviously the back end of that is all about where the services actually lie in terms of those trust services from CAs or HSMs, in terms of other IoT device management infrastructures, such as AVB's management platform, where they're doing more than just collecting the data and providing analytics. They're also providing the platform by which they can make changes to those architectures to reflect some of the decision logic that is being applied. Yep. There we go. So again, I'm making a presentation tomorrow if anybody wants to show up. We in Infineon, on behalf of the Industrial Internet Consortium, wrote a paper called Endpoint Security Best Practices, which is basically 13 pages of distillation of several thousand pages of compliance objectives. What we tried to do is put it together in such a way that it was easily consumable so that you can actually see how these types of technologies applied to platforms like ABB's actually make a difference. How the devices become more trustworthy and the data on those devices as trustworthy that can be used in those decision-making and decision support processes that are the back office architectures of why are we doing all of this. So endpoint security basic, endpoint security enhanced, these are all concept frameworks that are roughly equivalent to FISMA low, medium, and high, or equivalent to 62443, SL2, 3, and 4. And we'll talk more about that in my presentation tomorrow. And back to Joe.
All right.
That was a lot of talking, sorry.
That's all right. Thank you. Thank you, Dean. I didn't realize this slide animated. Let me get it all on the same page. There we go. So the AVB Ability Platform and its high-level architecture is the brand name that we use to describe how all of this is supposed to work. And we've got down here at the very bottom, you can see connected devices, whether they're enabled at the device level, or we've got some sort of a gateway or an edge device in front of it, or it's even on the customer premises, and then where we can bring that to the next level up and start performing analytics at either the factory level or the device level, and eventually getting those to the customer so we can make informed decisions. And as we described earlier, there are numerous use cases around this in the utility industry alone. Asset performance management seems to be the most compelling right now. I would say right behind that is workforce management and optimizing how we're deploying people and assets that need to be mobile. Whatever that might be, trucks, equipment, people, service technicians. And we take it the next level, and this is where at the device level, the Mocana technology helps us to secure that.
So what we're seeing in the industry, particularly with customers like ABB, is a need, is a desire, probably based on customer demand, to have a flexible architecture down at the device level. And the obvious way to do that is through things like containerization and virtualization, where the platform and the platform security are up through the hypervisor load, and then above that you have the containers or the VMs that are being deployed for specific functions. And again, to match up with all the things that Joe talked about, there may be performance enhancements, there may be operational enhancements, there may be maintenance enhancements. There's all kinds of things that may be deployed to these platforms in order to be use case specific. And then having the knowledge that those are trustworthy are also at issue. I've been arguing for better part of 20 years, just in virtualization and containerization, that we really needed a way to validate that those elements inside the containers or inside the VMs are trustworthy before we give them full access to the system. And that's been singularly unsuccessful up until recently. So what we've done is we've taken that base concept of platform security, and through remote attestation, we are then able to provide ABB and others like them the ability to validate the contents of the container before they give it full access to system privileges, or before they allow it to communicate with anything else. So basically we can take Docker 1, we can validate that it is a trustworthy build, meaning at the DevOps or the DevSecOps level that all the components were signed, that a trust chain was established, and that trust chain value was the expected value when we went and queried it. We issue it a nonce, and then we do the same thing for the second value. And the second VM or container is then also validated. And through that mutual authentication nonce mechanism, we actually then only allow trustworthy systems that have demonstrated themselves to be trustworthy to communicate with other trustworthy systems. And this could be in a single platform like a gateway. This could be in a single platform like a PLC. This could be in a multi-tiered platform where one of these was a PLC and the other one was a workload sitting in a cloud someplace at the back end of the analytics platform. The idea is that we can create trust values between these that can be shared effectively using strong cryptography so that we can establish communications between them based on a validated trust model. And that trust model is cryptography based, so it's hard to interrupt. The strength of cryptography is optional, right? If you want to do RSA 1024 and SHA-1 for size and performance reasons, good luck and God bless, and call me when it fails. If you want to do AES or ECC or some of the newer post-quantum technologies that are coming out, we stay at the forefront of those and are eligible to do a lot with some of the advanced algorithms and cipher suites. The idea of all this is that it's based on a hardware, firmware, or software root of trust. There's a system, there's a virtualization stack or containerization stack, support stack, and then there are elements that are brought into that to operate the actual componentry of whatever the objective of that particular platform is, if it's analytics out in the cloud, if it's ladder logic sitting in a PLC. That containerization and virtualization gives the vendor the flexibility to be able to make very rapid changes to the environment based on needs and desires and designs, while we in turn, at the back end of that, unobtrusively, using standards, can then validate that those are trustworthy constructs on the platform that they're designed to operate on, that they're not operating someplace that they shouldn't be, and that they're not inputting or outputting data any place that it shouldn't be coming from. Oh, I guess that one stole mine too. Okay. So again, this is all back to the whole concept of that life cycle. So how do we take it from the developmental stages, right? The pieces that go into an AVB piece of gear, some they manufacture, some they acquire from other sources. Some of the software they develop, some of the software they buy or pay to have implemented. We want all of those components to be signed and hashed at whatever strength is appropriate for the security model that you're trying to get to. We need to be able to convey those through the manufacturing process so that all the elements of the platform, whatever that is, if it's a cloud platform, if it's an actuator out in the field, doesn't matter. We want to build trust into each and every one of those elements. We want to take that all the way through to device activation, meaning that AVB builds it, they get a contract to go build or to update a subsystem or a substation. They take the gear out, they put it in place. How do we know that it wasn't tampered in transit? These are the kinds of things where we have to identify the platform, we have to identify the platform security structure as being appropriate and untampered with before we turn it on and start using it, and then connect it to other trusted systems at the back end so that they can do all those wonderful cost-saving things that they do with the data that is being generated off of these platforms. We need to be able to update those platforms in secure fashion. We need to be able to manage those devices in secure fashion. What happens if one of those manufacturers has a loss of root certificate, right? Or, you know, SHA-1, the United States government's been saying don't use SHA-1 for 10 years. Who's the single largest offender of still using SHA-1? The United States government. Why is that? Because they can't get to the certificates to make the changes. They have no management capability of those certificates. In many cases, those root CAs have ceased to exist a decade ago. So how do you manage certificates in that model? How do you manage the elements of the certificates, the PKI architectures that are associated with them? And the answer is, you don't. You live with what's there. Well, Mocana has a solution for that. And we recognize that we are standing between you and drinks.
Cocktail hour.
So we're happy to take questions now. We'll both be around out at our booth or in the bar or wherever you need us. If you want to grab us individually, we'd be happy to have a conversation. I want to thank Joe for participating with me.
Significance of having a TPM in there versus any other ideas?
Sure. So at the end of the day, what we were just asked is whether or can we differentiate why a TPM would be used in this environment, and what is the value of using an approach like this to build containerized or virtualized security at the VM or container level. So backing up a little further, when we talk about compromise and compromise to the hardware and supply chain, that's I won't say it's a finite group of elements, but it is a relatively finite group of elements. When you get into DevOps and DevSecOps and you get into all the components that can go into a VM or a container, the sky becomes the limit. So back to the expansion of the attack surfaces in the VMs or the containers expands exponentially. And secondarily, in today's world, for the most part, you have to fully instantiate that VM or that container prior to knowing what's in it. So you're going to give that container or that VM full access to the platform with all system services before you know whether it's good or not. Now, you can sign the shell and say that the shell is good, but that's not going to tell you what the contents do. And that's for VMs or containers. There's some other technologies that are out there that are starting to look at some of those values. Our particular approach to this and the approach that we're doing with our partner AVB is we're actually going to validate those using a cryptographic means. So when you build the container, when you build the VM, you're going to create an internal trust architecture to that VM. That trust architecture is going to have a known top-level value. It's the endorsed value of all the signed elements inside the VM. When that container or that VM goes out onto a platform, a target platform, and the platform itself is already trustworthy, we have TPM through hypervisor load measurements that we know are good, then we can look into the container at instantiation, and we can say, are all the values in that container the values we expect to see cryptographically matched? And if they are, then we have a good container or we have a good VM. If they aren't, then we don't. You can reinstantiate another container or another VM. You could send that off to isolation so that you can forensically analyze what went wrong. You can run it anyway and decide that the value of having it running exceeds the value of having it running securely, although I wouldn't advise that. I can think of a half a dozen scenarios in an industrial environment where that just might be the case. Right? If I don't have redundancy and I can't fail over to a security or a safety subsystem, then I got to run because lives are at stake. So, there's all different kinds of models here about how you take that decision and put it into what are we going to do next now that we know that it's good or it's not good. But the whole purpose is to know that it's good, because whether it's hardware generating data or virtualized or containerized elements generating data, we still want to know, is the data being generated trustworthy? Because if we don't know that, how do we base the decision on what we're going to do for automated maintenance, for all the cost savings that Joe talked about that AVB is demonstrating to the industry that their analytics platforms can do? If we can't tell you beyond a shadow of a doubt that the data is trustworthy, then we can't really trust the data to make those kinds of decisions. Or we can make those decisions and not really know if they're the right decisions or not. And swag. Does that make sense? And does that answer your question?
Right.
Thanks for coming. Welcome to come see us tomorrow.